Okay, hello again. This is Dr. Hanaa Assil, and today we're talking about a final review for paper 2C for the IGCSE Edexcel chemistry. Today we're talking about the topics that were not included in 1C. Remember that paper 2C includes everything. Some of the topics were in paper 1C. We're discussing the rest of the topics in 2C. So one of these topics is solubility curves. So he will give you a graph in which he shows the solubility in 100 grams of water for different solids at specific temperatures. So for example, he would tell you that he measured a certain amount of solid A and he dissolved it, heated it to a certain temperature, and then allowed it to cool. And when crystals start to form, that is when the solid has stopped dissolving. So we measure the amount that has dissolved per 100 grams of water at that temperature. So from the curve, what can we be asked about? For example, here I have solid A and solid B. He could ask, for example, at what temperature did both solid A and B have the same solubility? So to have the same solubility, this is the temperature at which they intersect. So this, from this graph, it is about 52 degrees Celsius. So at 52 degrees Celsius, both solids had the same solubility. Or he could ask something like this: at 40 degrees Celsius, which one was more soluble? So if you look at 40 degrees Celsius, which one was more soluble? I had more of B dissolved than A. So B was more soluble at that temperature. In another question, he would say, at high temperatures, which solid is more soluble? Of course, as you increase the temperature, more of A dissolved. So A had more solubility at higher temperatures than the others. Which one the temperature does not affect its solubility? Of course, if you look at solid C, at all temperatures, it has the same solubility. So increase in temperature does not affect the solubility of solid C. So basically, just get the information from the curve that he gives you. Then another topic is preparation of salts. And we said in order to prepare salts, we have to be aware which solids are soluble and which solids do not dissolve in water. So, for example, you should know that all nitrates are soluble. Sodium, ammonium, potassium salts are all soluble. All acids are soluble. Barium chloride, magnesium chloride, calcium chloride, all of these are soluble. Copper sulfate is soluble. So these are the things that we use in our syllabus. Now, what is insoluble? We said most carbonates are insoluble except for the sodium, potassium, and ammonium salts, of course. So barium carbonate, for example, is a precipitate when we try to prepare it, so it is insoluble. Calcium carbonate is insoluble. The silver halides and lead halides are insoluble. Barium sulfate, copper oxide, all metals, please be familiar with all of this, because the method that we use to prepare a salt depends on the solubility of what we're trying to prepare and the solubility of the reactants. So if I use titration, then I'm trying to prepare a soluble salt from soluble reactants. So when everything is soluble, reactants and the product, then I use the method of titration. If I am starting with something that's insoluble, so I'm preparing soluble from insoluble, then the method I use is called neutralization method. If I'm trying to prepare an insoluble salt, so the substance I'm trying to prepare is insoluble, I do precipitation, because when I add two solutions, it will precipitate out. So what do we do in each of these? So if he's telling me, for example, he wants to prepare sodium chloride. Now, the first question that you ask yourself is sodium chloride soluble? Yes, we said all sodium salts are soluble. Okay, the second question is, What am I going to start with? Well, in order to prepare sodium chloride, then I will need sodium something and something chloride. So the base sodium hydroxide and the acid HCl. If I add them together, it should give me sodium chloride solution. But the problem is you should add a certain amount of sodium hydroxide to a certain amount of HCl in order to neutralize the solution without having any of them excess. So I don't want to add too much sodium hydroxide and I don't want to add too much HCl. That is why we do titration. So the basic idea of doing titration is I'm trying to find out how much of each of these I should add. So you should be able to explain titration to prepare, for example, sodium chloride from sodium hydroxide. And the first thing you do is put 25.0 centimeter cubed of the base solution, sodium hydroxide solution, in a flask using a pipette. Again, when you're trying to explain to him how to make any experiment or how to prepare a salt, you have to explain in detail and include the apparatus that you're going to use. Then we add 3 drops of phenolphthalein. You should know that phenolphthalein on sodium hydroxide is pink. Or you could use methyl orange. Remember, we never use universal indicator in titrations because universal indicator has different colors at different pHs. I want something that has a specific color that will turn from something to something. So add 3 drops phenolphthalein, the solution turns pink. Add dilute HCl from the burette until the pink color turns colorless. Note the amount of acid used. Then the idea was trying to prepare sodium chloride salt. Then I'm supposed to, now I know how much acid I should add to the base. I'm going to repeat by adding the required amount of acid to 25 centimeter cubed of sodium hydroxide without using indicator. Remember that first flask had phenolphthalein or methyl orange. Heat the solution to point of crystallization, cool, filter the crystals, wash with a few drops of distilled water and dry between filter papers. If he's saying prepare pure dry crystals. This we've mentioned before and you should keep in mind. He can ask you about the process of titration itself. When doing a titration, you should remember that I should be holding the flask with one hand and adding from the burette with the other hand. That is because the flask should be swirled and it should be on a white paper or a white tile to see the color change clearly. Then when reading a burette, the eyes should be on the same level as the meniscus and we read the bottom of the meniscus. And when we do titrations, we usually wash the burette twice. We wash it once with water to remove traces of any previous solution. Then with the solution I'm going to fill it with to remove water, which could change the concentration of the solution. Or he could ask you to explain the process of titration itself. So here this was a question with 4 marks saying describe how to use the apparatus to find the volume of sulfuric acid needed to neutralize sodium hydroxide. So he's saying you should explain the process of titration itself. And you should know when we do titration, we put 25 centimeter cubed of sodium hydroxide into a flask using a pipette. Add 3 drops. In this case, I was using methyl orange. Remember we said it could be methyl orange or it could be phenolphthalein. Here he was actually specifying methyl orange. Fill a burette with dilute sulfuric acid. Note the initial reading of the burette. Add acid from the burette until, because this is methyl orange, yellow solution becomes orange. Note the final reading of the burette, subtract the final minus the initial to obtain the volume of acid used, and then repeat to obtain concordant results. This is how you explain titration, the process of titration itself. Now, what are concordant results? Remember, when you do titration, we repeat several times. So this is a student that repeated the titration several times. You should know that concordant results are those within 0.2 centimeter cubed of each other. That means the difference between them should not be more then 0.2. So which of these volume of acids in this table are concordant? Can you see 25.1, 25.3, 25.2? All of these are within 0.2, so these are the concordant results, and this is what I use to get the average. When he says get the average, I add the concordant results and divide by their number. So here I have 3 of them, so I divide by 3, and that means that the average volume of acid used in the titration was 25.2. The other method of preparing salts is neutralization. Neutralization is if I am trying to prepare a soluble salt, but what I start with is insoluble. So here, for example, I'm trying to make copper sulfate. Now, in order to make copper sulfate, what should I start with? Well, I need acid, sulfuric acid. And then I need a base, but the copper oxide is insoluble. Remember, I cannot say copper plus sulfuric acid. Copper alone will not react with acid. But copper oxide is a base, so it will react with the acid. So how do we do this? We said the first thing we do is we add the solid copper oxide using a spatula to 25 centimeter cube sulfuric acid in a beaker until excess solid remains in the beaker. Filter through filter paper and funnel. If he says, why are we using excess solid? Why are we adding excess copper oxide? Remember, we need to add excess copper oxide to make sure that all the acid reacts. Then we filter through filter paper and funnel. Why are we filtering? To remove the excess solid that we don't want. So the excess copper oxide will be collected as residue. Then we take the filtrate, which is now copper sulfate solution, and we do crystallization. So heat the filtrate to point of crystallization, cool, filter the crystals. The other method is precipitation. In precipitation, we're trying to make something that's insoluble. So silver chloride, for example, is insoluble. That means I need to start with 2 solutions that are soluble. Remember, to make silver chloride, then I need silver something that is soluble. And we said all nitrates are soluble, plus sodium chloride, or I could use HCl if you want, but sodium chloride is good enough because I know that sodium salts are soluble. Now, when we add these 2 solutions, and both of them have to be solutions, silver nitrate and sodium chloride. So if he says he's starting with them solids, then you have to dissolve them in water first, then add the 2 solutions in a beaker. So this gives a white precipitate. Silver chloride forms as a white precipitate. This is what I want. So I filter it, and the residue is what I want. Wash the residue with a few drops of distilled water. Dry the residue between filter papers. Then the other topic that comes a lot in 2C is chemical calculations involving moles. And you have to know these 3 main equations. Please learn them. To get number of moles, I can either use mass over molecular mass, or volume over 24, or concentration times volume. Now, when do we use each of these? Number of moles is mass over molecular mass if he gives me mass. So if he gives something in grams and he says get the number of moles, then the number of moles is mass over molecular mass. And in that case, if I want mass, mass is number of moles times mR. But then if we're talking about volume of gases, then number of moles is volume over 24. So number of moles is volume over 24 I use for gases. So remember, the volume has to be in decimeter cubed. If he gives me something in centimeter cubed, I have to divide by 1,000. Now, if from this equation I want to get volume, then volume is number of moles times 24. Or if we're talking about solutions, so if he's talking about sodium hydroxide, HCl, and so on, then the number of moles is concentration times volume. Again, the volume in the equation has to be in decimeter cubed. So if it is in centimeter cubed, you have to divide it by 1,000. And from that equation, if he's asking for concentration, then concentration is number of moles over volume. Please learn these. Another topic that was not included in 1C is reversible reactions and the effect on conditions, different conditions on equilibrium. So First of all, you remember that reversible reactions are reactions that go both forward and backward without going to completion. So a reaction that goes forward and then the products break up to give reactants, and then the reactants react again and give products and so on, that's a reversible reaction. And we said, how do we know it's reversible? If he gives that double-headed arrow, that indicates that the reaction is reversible. And we said a common example was when we have hydrated copper sulfate, which is copper sulfate with water in it. If I heat it, it turns from blue to white. If I add water to the white, it becomes blue again. So this is a reversible reaction. And then we said a reversible reaction will keep going forward and backward until it reaches what? Until it reaches equilibrium. And if he says what is meant by equilibrium, equilibrium is or the state of equilibrium is when rate of forward reaction equals rate of backward reaction and concentration of reactant products remain constant. So that means the rate of the forward reaction is equal to the rate of the backward reaction. And concentrations of reactants and products remain constant. Don't say they are equal, for example. They're not equal, they're just the same. The same amount of reactants, the amount of products does not change, the amount of reactants does not change. So if I have something like this, NO2 is brown, if it becomes N2O4, it's colorless. At equilibrium, it is somewhere in between. So the reaction does not stop, the reaction is just going the same rate forward and backward, and the reactants and products are constant amounts. But we can change conditions in order to cause the reaction to go forward or backward, or for the point of equilibrium to shift to the right or to the left. One of the things that we can change is pressure, but remember that this pressure affects only gases. So I can use it in this Haber process because they are all gases. So what happens if I increase the pressure? Please learn with me. Increasing the pressure in a reversible reaction will cause it to go to the side that has less number of moles or less number of molecules. So in this reaction, if I increase the pressure, that means I'm pressing all the gases near to each other. They will want to relieve this pressure and they will go to the side that gives less molecules. Now, which side gives less molecules here? If I go forward, it gives 2 moles of ammonia. If I go backward, it gives 1 mole of nitrogen and 3 moles of hydrogen. That's a total of 4 moles. So increasing pressure in this case, if he says what is the effect on the point of equilibrium, it shifts to the right or the reaction goes forward. Now, what is the effect on the yield of ammonia? We said in this case, if the reaction goes forward, that means I get more ammonia. So it will increase the yield of ammonia. Another thing we can do is changing the temperature. And I want you to remember, increasing the temperature of a reversible reaction causes it to go to the side that is endothermic. If I increase the temperature, that means I raise it, I heat it up, it will try to lower its temperature. So it will go to the side that is endothermic. Remember, when you have a reaction like this and he says delta H is negative, that means that the forward reaction is exothermic, and that means the backward reaction is endothermic. So if I increase the temperature, what happens here? We said increasing the temperature causes the reaction to go to the side that is endothermic. So in this case, if I increase the temperature, it goes backward. What is the effect on the yield of ammonia? That means it will give less yield of ammonia. Adding more reactants or removing products. If I add more nitrogen, more hydrogen, or I remove the ammonia as it is formed, then this causes the reaction to go forward. So this gives me more ammonia. Okay? Effect of catalyst on the point of equilibrium. Remember, we have effect of all of these things on one of 2 factors. Either he's saying what is the effect on rate, and that's something else, or what is the effect on the point of equilibrium. Then in that case, you tell me it will go forward or backward, or shift to the right or shift to the left. So catalyst speeds up both forward and backward reactions. So when I add a catalyst, that does not cause the reaction to go forward or it does not cause it to go backward. It has no effect on the point of equilibrium, and that means it will have no effect on the yield. It doesn't give me more ammonia if I add catalyst. It just makes the reaction overall faster. The other topic is energetics, and you remember that exothermic reactions are reactions that give out heat, and they give out heat to what? To the surrounding solution. That means the surrounding solution becomes hotter and the temperature of the solution increases. Remember that all combustion reactions or burning reactions are exothermic. Now, endothermic means the reaction takes in heat from the surrounding solution. So the surrounding solution becomes colder, the temperature decreases. Remember that changing from solid to liquid to gas is endo. In order to change from solid to liquid, I have to heat the solid, so the solution takes in heat. So going from solid to liquid to gas is endo. Going from gas to liquid to solid is exo. Then he will ask you to draw one of two things. Either he will tell you to draw the reaction profile diagram, and remember that the reaction profile diagram includes activation energy, or he will tell you to draw the energy level diagram in which there is no activation energy. So for an exothermic reaction, remember activation energy is always from reactants to the top. The delta H is always from reactants to products. In an exothermic reaction, where are the products? Above reactants or below reactants? You should realize that exo means the reactants lost some of their energy, and that means the products have lower energy than reactants. So in an exothermic reaction, the products are below. And that means activation energy from reactants to the top, delta H from reactants to the bottom, which is the product. If we're drawing energy level diagram, you just indicate that the delta H is from reactants to products. An endothermic reaction, the reactants take in heat. That means the products will have more heat, and that means the product will have higher energy than the reactants. But also, where is activation energy? From reactants to the top. Where is delta H? From reactants to products. But of course, for the endothermic reaction, the delta H is a positive value. For exo, it was a negative value. Okay. Then he will give you a question about bond energies. Remember, we said in order to calculate delta H, we have one of two methods. There was one method that was included in paper 1C, which is the one that we use Q is equal to MC delta T, and then we get delta H. But the other method is if he gives me bond energy. So for example, if I have this kind of question, I have hydrogen plus chlorine to give 2 HCl. In order for this reaction to happen, I need to give it energy in order to break the bonds in the reactants. So I need to break the bond between the H and H and the bond between the Cl and Cl, and then I will be forming 2 HCl bonds. Remember that to break a bond, you need to give it energy. So the reaction takes in energy. So bond breaking is endothermic. Now, when bonds form in the products, they release energy. So bond formation is an exothermic process. Now, overall, is this reaction exo or endo? Well, that depends. If the amount of energy taken in to break the bonds in endo is more, to break the bonds in the reactants is more than the energy released when the products are formed, then overall I'm taking in more energy, then overall the reaction is endothermic. But if I take in energy to break the bonds in the reactants, but when the bonds in the products form, they give in more energy, then overall the reaction gives energy, and overall the reaction is exothermic. So, for example, he will give you the bond energies for these bonds and then ask you what is the overall delta H. You have to remember that the overall delta H is the reactants minus the products. So in order to break the HH bond, I add 436. To break the Cl-Cl bond, I add 242. But when I form two HCl bonds, each of them will give out 431, so it will release 2 times minus 431. Now, the reactants minus the products, that will give delta H. So overall, my delta H for this reaction is minus 184. This is because it gives out more than what it takes in. So this is an exothermic reaction. Okay, so heat is lost to the environment. Organic chemistry. We already talked about organic compounds when we were talking about 1C. We said organic compounds are covalent compounds of carbon that were originally obtained from plants or animals. And we said that alkanes, for example, have this kind of structure with only single bond C. So if we look at the formula, the general formula for alkanes was CnH2n plus 2. They all have C single bond C, so we say they are saturated, and we say that the functional group of alkanes is C single bond C. Alkenes, these are the different types of alkenes. They all have C double bond C. If we look at their formula, you will find that the hydrogen is always twice the carbon, so we say the general formula is CnH2n. They all have C double bond C, so that is why we refer to them as unsaturated, and we say that the functional group of alkenes is C double bond C. We said we divided organic compounds into different groups. Each is referred to as a homologous series. The members of the same homologous series have the same general formula, same functional group, same chemical properties. Hydrocarbons are alkanes and alkenes. We refer to them as hydrocarbons because they are made up of carbon and hydrogen only. To name organic compounds, we already mentioned you have to determine the number of carbons and then determine whether it's an alkane or alkene or alcohol or acid in order to determine its name. So we talked about all of this. Please refer to the previous video on paper 1C. Types of formulas, we said if he says displayed formula, that means you have to draw it out with all the bonds and all the atoms. Structural formulas, you collect the hydrogens around each carbon. Molecular formula means you count the total number of carbons, total number of hydrogens, and so on. Isomers are two or more compounds having the same molecular formula, different displayed formula. So we said if I want to draw isomers of propanol, we said propanol is something that has 3 carbons. All means it's an alcohol. Now the isomer would be, where is the OH? So I can put the OH on one end or I can put it in the middle. And this means that these two have the same molecular formula but different structures, so these are isomers. If he says draw isomers of butene, butene is something that has 4 carbons with a double bond. Now, are we putting the double bond on one end or the double bond in the middle? So these are the 2 isomers. If we're drawing isomers of an alkane, we said pentane, for example, you can either put the 5 carbons all in a row, so we say this is a straight chain, or a branched chain where you put 4 in a row and then one of them is attached somewhere in the middle, or 3 carbons in a row and 2 of them attached in the middle. Alkanes below 5 carbons are gases, and then as the number of carbons increases, it becomes liquids and solids. Uses of methane, we said it is used as a fuel, and you should remember that methane is the main constituent of natural gas. The reactions, alkanes, alkenes, and alcohols all do combustion. We said excess oxygen gives carbon dioxide plus water. Incomplete combustion or lack of oxygen will give carbon monoxide plus water. And we said carbon monoxide is poisonous because it reduces the capacity of blood to carry oxygen. You should know all of this for paper 1C. Substitution reaction of alkanes, we said when we have alkane with halogen, this is called substitution reaction. The condition needed is UV light. Now what happens is I remove one of the hydrogens and I place a chlorine instead of it, or I place a bromine instead of it. The other product would be the HCl or the HBr. And we said we can remove any of the hydrogens and replace it, just one of them, and replace it with a hydrogen. Okay, so far? What is cracking? Breakdown of long chain hydrocarbons into shorter chains. Conditions for cracking: aluminum oxide catalyst in 600 to 700 degrees Celsius. Alkenes do addition. Remember we said alkanes do substitution, but alkenes do addition. So the double bond opens up and you put something on each side of the double bond. So reaction with bromine, we said this is the test for alkenes. It changes from orange to colorless. So that is the test for alkenes. Alcohols. Now, alcohols, acids, and esters were not included in paper 1C, so please concentrate on them for paper 2C. First of all, functional group of alcohols is OH. You should remember one carbon is methanol, ethanol, propanol. Remember that the one propanol indicates that the OH is on the first carbon. First carbon means on one end from this side or one end from the other side. In both cases, we call it one propanol. This is one butanol. Here it is butanol, but the OH is on the second carbon, so this is 2. Uses of ethanol. Remember that ethanol is used as fuel, as solvent, to make beer, to make perfumes. How do we prepare ethanol? You have to remember, in order to prepare ethanol, I use one of two main methods. The first method is what we call hydration of ethene. So in this case, I start from ethene, I add water, phosphoric acid catalyst, 300 degrees Celsius, 60 to 70 atm pressure. That changes ethene into ethanol. Now, where do we get ethene from? We get it from petroleum or crude oil. So we said that fractional distillation of petroleum and then cracking gives ethene. Then the other method of getting ethanol is from glucose. So if I have glucose, I add yeast, water, 37 degrees Celsius or 35 degrees Celsius. This is called fermentation of glucose, and it changes it into ethanol and carbon dioxide. Where do I get the glucose from? I get it from sugar cane. Now, it's very important to realize the advantages and disadvantages of each of these methods. Now, hydration of ethene, when I add water to ethene or we add steam to ethene, what are the advantages? Remember, if I add steam to ethene, the only product is ethanol. So it produces a pure product. It's a fast process. It does not produce CO2, so it does not contribute to greenhouse effect. So these are the advantages of hydration. Now, what are the disadvantages of this method? We said I get ethene from crude oil, and that is a non-renewable resource. And we need to do it at high pressure and high temperature, 60 to 70 atm, 300 degrees Celsius. So this is more expensive. Now, if we're doing fermentation of glucose, we said glucose is obtained from sugarcane, and that's a renewable resource. And then all this process is done at room temperature and pressure, so it is less expensive. So these are the advantages of fermentation of glucose. The disadvantages would be that this process is slow and it produces ethanol that needs to be purified, because at the end of the reaction, I have a mixture of yeast and water and the ethanol. So first of all, I need to filter to get rid of the yeast, and then do fractional distillation to separate the ethanol from the water. In addition to that, this process produces carbon dioxide, which contributes to greenhouse effect. Reactions of ethanol, of course, like alkanes and alkenes, it does combustion. Complete combustion will give carbon dioxide plus water, and incomplete combustion gives also carbon monoxide plus water. The other reaction of ethanol is oxidation of ethanol. Any alcohol can be oxidized to give the corresponding acid. So if I oxidize ethanol, it gives ethanoic acid. If I should do that to propanol, it would give propanoic acid, and so on. Now, how do I do oxidation? I add potassium dichromate and sulfuric acid. So these are the conditions or the reagents that we add in order to oxidize an alcohol to an acid. Potassium dichromate is originally orange. When we react it, it changes from orange to green. The other reaction of ethanol is dehydration. I can remove H and OH from the ethanol to change it to ethene. So what are the conditions for this? I put aluminium oxide catalyst and heat. So notice, aluminium oxide is a catalyst for two processes. We used it as a catalyst for cracking, and we're using it as a catalyst for dehydration of ethanol. Acids, you should be familiar with acids. They have C double bond O, single bond OH. So the one that has one carbon is methanoic acid, ethanoic if we have two, propanoic acid, and so on. Remember, you need to count the total number of carbons, so including the one that is attached to the double bond O. So propanoic acid has a total of 3 carbons. Now, what are the reactions of acids? Well, these are acids. Ethanoic acid is an acid, so it will do the reactions of acids. For example, reaction with metals. So with metals, the ethanoic acid would give hydrogen gas, and the product that is formed is something ethanoate. So with sodium, it would be sodium ethanoate. We remove the H of the COOH, that is the acidic hydrogen. We remove it and we put the metal, sodium, for example, instead of it. If I'm reacting with calcium, remember calcium has a valency of 2, react with 2 molecules of ethanoic acid, so we get this calcium ethanoate plus hydrogen. Again, as a normal acid, it would react with carbonates to give carbon dioxide plus water. Again, we remove the H of the ethanoic acid and we put Na, and that is sodium ethanoate plus carbon dioxide plus water. Now, the other reaction that you need to be familiar with is to form esters. Alcohols react with acid to form esters. So if I start with ethanoic acid, I react it with ethanol. First of all, you have to remember what are the conditions of this reaction. It's concentrated sulfuric acid. So when I'm trying to form an ester from reaction of acid with alcohol, I need to do that in presence of concentrated sulfuric acid. That's my catalyst. So we say ethanoic acid plus ethanol. I remove the OH from the acid. I remove the H from the alcohol and I join them together. And when we draw the ester, we start by drawing the acid. So I started with ethanoic acid. So I started drawing the C with 3 hydrogens, C double bond O, and then I attach the part from the alcohol, which is the OC2H5. So that is the diagram or the structure of the ester. Now, what is the name of that ester? To name the ester, we start from the name of the alcohol. Now, which alcohol did we start with? We started with ethanol, so the name of the ester should start with ethyl. Now, which acid did we start with? Ethanoic, then it is ethyl ethanoate. So the one that has OH at the end, that was the acid. The one that is ethyl, that was the alcohol. Let's try again. We want to react propanoic acid with ethanol. Again, I want to join them together. I remove the OH from the acid, remove the H from the alcohol, and join them together. Then, when I want to name it, what would be the name of that ester? Which alcohol did we start with? Ethanol. Then the name is ethyl something. Then the acid was propanoic acid, so this is propanoic So it's ethyl propanoate. Of course, the other product of this reaction is water. If we remove the H and OH, then the other reaction is water. Remember again, the conditions for this reaction is concentrated sulfuric acid. Again, let's try to name esters. So this is an ester, C double bond O, O something. Now, how am I going to name this ester? We said we look for the alcohol part. So which part was the alcohol? This one was the alcohol, the one after the O something. So this is one carbon, so the name of this ester should be methyl something. Now, where is the acid part? This is the acid part, the part that has the C double bond O, that was the acid. So this was made from which acid? An acid with two carbons. So that is ethanoic. That means this is methyl ethanoate. Again, let's try this one. How are we going to name this ester? Where is the alcohol part? This one. How many carbons? Two. So the name should be ethyl something. Where is the acid part? Has only one carbon. So this is ethyl methanoate. You start with the name of the alcohol with an "il", and then the name of the acid with an "oate". Again, let's try this one. Where is the alcohol part? Two carbons, so that is ethyl. The acid part also two carbons, so this is ethyl ethanoate. Are we following? This one, where is the alcohol? The part after the C double bond O. How many carbons? Two. So this must be ethyl something. Then where is the acid? That's the acid. Four carbons. So this is ethyl butanoate. Are we following? This is very important for paper 2C. So this is a typical question. He says, give the name and formula of the two compounds formed when this ester ethyl propanoate is hydrolyzed. Remember, hydrolyzed means broken down back into its acid and alcohol. So if I have an ester, I can break it down, react it with dilute acid, break it down, and it will break up into the original alcohol and acid. So what was this made from? It was made from this part. This part was which one? The one that has C double bond O, that was the acid. So this is an acid with three carbons. And this was the part that was alcohol. So this was made from propanoic acid, which looks like this, and ethanol, which is this. Please try to practice all of this. If I say write the word equation, I react methanol with ethanoic acid. What do you think this should give me? Of course, this is alcohol with acid, so it should give the ester. What would be the name of the ester? Methyl ethanoate. Plus what? Plus water. Write a word equation for the preparation of the ester butyl methanoate. So I'm trying to make butyl methanoate. So this was made from which alcohol and which acid? We said the butyl is the alcohol part. So that was made from butanol. Methanoate means it was made from methanoic acid. So butanol and methanoic acid gives this ester plus water. Write the word equation for the preparation of the ester propyl ethanoate. Again, I'm trying to make propyl ethanoate. I will make it from what? Propyl means I started with propanol. Ethanoate means I started with ethanoic acid. So this will give propyl ethanoate plus water. Deduce the structure of this ester. How would we draw propyl ethanoate? We said when we draw, we start with the acid. This was made from ethanoic, so I draw an acid with two carbons, C double bond O, O, and I remove that final H. Instead of that, I'm going to put the part of the propanol. So this is propanol with three carbons, so this is propyl ethanoate. Write an equation to show what happens when ethanoic acid is dissolved in water. Remember, any acid ionizes in water. So if we say we're dissolving ethanoic acid in water, it will ionize. But for the organic acids or the carboxylic acids, it is that final H that breaks up to form H plus. So it will form CH3COO minus plus H plus. Ethanoic acid reacts with ethanol to form an ester. If I react ethanoic acid with ethanol, what would be the name of the ester? Ethyl ethanoate. Draw the displayed formula of the functional group in esters. So he's not telling you to draw the ester, he's saying draw the functional group in esters. Remember that all esters will have C double bond O, single bond O. That's the functional group of esters. What do we use esters for? Remember, esters have a fruity smell and a nice taste, so the food flavorings or in perfumes. The other topic is polymerization. Remember that we have two types of polymerization. The part that was included in 1C was the addition polymerization, where I start with monomers that have C double bond C. And in that case, my polymer was the only product. But in condensation polymerization, I'm starting with two different monomers that have functional groups on both ends. And we remove H and OH, so we remove small molecules such as water when we do condensation polymerization. So what is condensation polymerization? We said we start with something that has acids on both ends. So we call it a diacid. And then another thing that has alcohol groups on both ends. So that's a dialcohol or diol. We join them. When we join them together, we're trying to form polyesters. Now, how do we join them? We remove the OH from the acid, we H from the alcohol. OH from the acid and H from the alcohol, and join. So if he says draw the structure of a polyester or the structure of pterylene, it is C double bond O box C double bond O, O box O. Of course, the other product is, remember that we said there are natural polymers and synthetic polymers. Polyester is a synthetic polymer. You should remember that things like carbohydrates, proteins, fats, these are natural polymers. You should also remember that polyesters are usually non-biodegradable. We said one of the problems of polymers is that they are non-biodegradable, so they cannot be broken down by bacteria. But there are other polymers which are called biopolymers. These are polymers that can be broken down by bacteria. So this, for example, he says, what type of polymer is this? Now, of course, this is not something that I started from an alkene, so it's not an addition polymer. It's something we used acids and alcohols to make, so this is a condensation polymer. And then he says, give the structures of the two monomers from which the polymer was made. So this polymer that you have on top there, it was made from what? You should realize that this is the polymer after it was joined. Now, it was made from what? Well, it was made from a part that has C double bond O. So that is the part that was acid. So it's now C double bond O, OH. And the part that had O on both ends was the part that was alcohol. So this was the part that had OH on both ends, and then we removed the H from the alcohol and the OH from the acid, and we joined to get that polymer on top. Another topic that was not included in 1C was electrolysis. Remember, electrolysis is the breakdown of an ionic compound, molten or in aqueous solution, by the passage of electricity. We said we have an electrolyte, which is molten or aqueous ionic compound that conducts electricity. And we have two rods, which we call electrodes. The electrodes are rods that can conduct electricity. So these electrodes are usually made of graphite or platinum. And we said graphite is better because it is cheaper than platinum, but both of them are inert electrodes. Then we connect these electrodes to the ends of the battery, one to the positive end of the battery and one to the negative end. The one that is connected to the positive end of the battery is connected with wires that have electrons in them. Now, the electrons in the wire will be attracted to the positive end of the battery, so they will pull electrons from that electrode. That electrode becomes positive. The other electrode that is attached to the negative end of the battery, the electrons will be repelled from the negative end of the battery to the electrode. So that electrode will have a lot of electrons on it. So that's the negative electrode. Now, the negative electrode attracts positive ions, which are called cations. So the negative electrode is called cathode. The positive electrode will attract the negative ions in the electrolyte. Negative ions are called anions, so the positive electrode is called anode. So remember, the electrode attached to the positive is positive, and that is the anode. The electrode attached to the negative end of the battery is negative, that is the cathode. This is an experiment to distinguish between electrolytes and non-electrolytes. If you want to know if something is an electrolyte or not, again, we said what's an electrolyte? Electrolyte is something that conducts electricity. So we say set up a circuit as shown. If I put something, remember the circuit has a light bulb. If I put something that conducts electricity, the light bulb goes on. So if I put solid sodium chloride, the lamp does not light up. Remember that solid ionic compounds do not conduct electricity because the ions are not free to move. If I dissolve the sodium chloride in water, the bulb lights up. So that means that the ions are free to move in the solution, and that conducts electricity. If I put a solution of something that's not ionic, like glucose, of course, this is something that does not have free ions in it, so it does not conduct electricity. The lamp will not light up. And then we said if we set this up, you should remember which one goes to the cathode. The cathode is the negative, so the positive ions go to it. Now you should know that metals or hydrogen are usually positive ions, and these are the ones that go to the cathode. The non-metals usually form negative ions and they go to the anode. So your job would be to determine what happens at each electrode for each kind of electrolyte. So if we're doing electrolysis of molten sodium chloride will have which ions? It will have Na plus and Cl minus. The Na plus will go to the negative and the Cl minus will go to the positive. Now the Cl minus, when it goes to the positive, it loses electrons. Any negative ion goes to the anode to lose electrons and become atoms. Then the atoms join together to form molecules like Cl2. So if he says name the product at the anode, it's chlorine. What is observed at the anode? What does chlorine look like? It's a green gas. So if he says what is observed at the anode, it's bubbles of green gas. On the other end, Na plus goes to the negative. Now, Na positive goes to the negative to gain electrons. And when it gains electrons, then it becomes the atoms. So in this case, to become the metal, and we have sodium depositing. So we will see a gray, silvery gray metal forming at the cathode. What if we're doing electrolysis of molten lead 2 bromide? Again, what ions do I have? I have lead 2 plus and Br minus. The Br minus will go to the anode and lose electrons. So it will form bromine. And I will see, or the observation would be reddish brown fumes. The lead 2 plus will go to the negative to gain electrons and become lead metal, so it will appear as a gray metal deposit. What if we're doing electrolysis of molten copper 2 chloride? Again, the same thing. It forms copper 2 plus and Cl minus. The Cl minus will go to the anode and lose electrons. So what is observed is bubbles of green gas. The copper 2 plus will go to the cathode, gain electrons, and remember that copper metal is a reddish brown metal or a red metal, will deposit. But then what if we're using solutions, not molten? So if I'm saying I'm doing electrolysis of concentrated HCl, now in this case I have H plus and Cl minus from the HCl and H plus and OH minus from the water, because now we have water. Remember molten, the other ones were molten. Molten means I just heated them until they melted, until they became liquid. But here we're dissolving them in water, so we have H plus and OH minus from the water. Now in this case, for each electrode, I have a choice. Because, for example, which ones will go to the positive? Well, both chloride and hydroxide ions will be attracted to the positive, but only one of them can react. Please pay attention. If I have a choice between chloride and hydroxide, the one present in higher amounts is the one that will react. So if I say that I'm doing electrolysis of concentrated HCl, which one do I have more of? I have more Cl minus. So that is the one that will react, lose electrons, and I will see bubbles of green gas. On the other end, I have H plus ions, no other positive ions, so the H plus ions will gain electrons and become hydrogen gas. Please notice the balancing of each of these half equations. These are the ionic half equations in the reaction. If I'm doing electrolysis of concentrated sodium chloride, again, I have Na plus and Cl minus and H plus and OH minus from the water. Again, I have a choice between chloride and hydroxide at the anode. Which one reacts? We said if we have a choice between chloride and hydroxide, the one present in larger amounts will react. So concentrated sodium chloride means I have more of chloride, so the chloride will lose electrons, become chlorine, and I will see bubbles of green gas, and this is how they make chlorine gas. At the cathode, I have a choice between Na plus and H plus. Now, if we have a choice between Na plus and H plus, the Na plus will not react because sodium is a very reactive metal. Whatever is a reactive metal will not react in electrolysis. So, choice between Na plus and H plus, it's the H plus that will react. So the H plus will gain electrons and become hydrogen. Now, if the chloride ions reacted and the H plus ions reacted, what is left in solution? I'm left with Na plus OH minus, so I'm left with sodium hydroxide in solution, and that means if I put a litmus paper or universal indicator, it will turn blue. What if I'm doing electrolysis of dilute sodium chloride? Again, which ions do I have? Na plus Cl minus and H plus and OH minus. Now we have a choice between chloride and hydroxide. Do you remember the rule? Choice between chloride and hydroxide. The one present in higher amounts reacts. Now I have dilute. What does dilute mean? Dilute solution means I have a lot of water. So it is the OH minus that is a lot. So it's the OH minus that reacts. I want you to remember, when the OH minus reacts at the anode, it gives oxygen gas, water, electrons. And when you balance it, you'll find that this is the balancing. So if he says what is observed, it is bubbles of colorless gas because oxygen gas is formed. On the cathode, I have a choice between Na plus and H plus. We said if we have this choice, which one reacts? The H plus will react. Na plus will not react. So what has happened to the solution? If OH minus reacted and the H plus reacted, that means I'm left with what? I'm left with, the water has reacted, so I'm left with a more concentrated solution of sodium chloride. I started with dilute. What has happened to the solution? It has become concentrated sodium chloride. If I'm doing electrolysis of aqueous copper sulfate, again, copper sulfate means I have copper 2 plus and SO4 2 minus, and I have H plus and OH minus. At the anode, I have a choice between sulfate and hydroxide. I want you to remember, sulfate will never react in electrolysis in our syllabus. So it is the OH minus that will react, forming oxygen, water, and electrons. On the other end, I have a choice between copper 2 plus and H plus. Again, we said, if it is a reactive metal, it doesn't react. But here I have a choice between hydrogen and copper 2 plus. So which one is more reactive, the hydrogen or the copper? The copper here is less reactive, so it is the one that will react. So copper 2 plus gains electrons and becomes copper metal. Are we following these rules? Dilute sulfuric acid. Again, you need to decide what are the ions. I have H plus sulfate 2 minus and H plus OH minus from the water. Again, if I have a choice between sulfate and OH minus, which one reacts? Hydroxide reacts to give oxygen, gas, and water and electrons. On the other end, I only have H plus ions that can react. Okay, please practice all of these. You will be required to write the ionic half equations. Then we have metals. We talked about the structure of metals. We said they are giant three-dimensional structure with regular rows of positive ions surrounded by a sea of free-moving delocalized electrons. That means if he says what is the metallic bond, remember we talked about ionic bond, covalent bond. Now the bond in a metal is called metallic bond. Now what is holding the metal together? It is the strong attraction forces between positive ions and negative delocalized free moving electrons. So this is what we call a metallic bond. It's attraction forces between what? Positive ions and negative electrons. Okay, and remember that we said metals have high boiling point and melting point because there is strong attraction forces between the positive ions and the negative electrons that need a lot of energy to be broken. Remember we said physical properties of all metals. All metals conduct electricity, all metals are malleable and ductile, and all metals are shiny. Remember, if we say why is it that metals conduct electricity? Because they have free electrons, free moving electrons. Metals are malleable and ductile because layers of positive ions can slide over each other when heated or hammered. Then you should know about the chemical reactivity series. We said rusting of iron. What happens in rusting? Remember, iron reacts with water and oxygen in order to rust. So if we add anhydrous calcium chloride, remember anhydrous calcium chloride is called a dehydrating agent. It removes water. So if there is no water, the nails will not rust. If you put the nails in boiled water means there is no oxygen. The oxygen has been removed, and then if we cover it with a layer of oil, no oxygen can dissolve. So that means there is no oxygen, then the nail will not rust. But if I put it in distilled water, normal tap water, any water normally would have some oxygen dissolved in it. So nails in distilled water would rust. Now, if we have salts like seawater, or if we have acid in the water, that makes it rust faster actually. And then when the iron reacts with the water and oxygen, what we call rust is actually called hydrated iron 3 oxide. So the rust is hydrated iron 3 oxide. And if we say what is the appearance of that, it is reddish brown and it is flaky. Flaky means it can be peeled off easily. And we said to prevent rusting, one of the methods is painting. I can either paint the railings or iron gates. And we said, how does that protect the iron? It provides a barrier that prevents the iron from reacting with oxygen and water vapor in the air. Or we can coat it with oil or coat it with plastic. All of these are the same method. They are forming barriers to prevent the iron from reacting with water and oxygen in the air. And that means if this layer of plastic or the layer of paint is peeled off, then the iron will rust. Galvanizing, it is covering the iron with a layer of zinc by dipping or spraying. Now, if he says, how does this protect the iron? We said this is because zinc is more reactive than iron, so it loses electrons and becomes oxidized instead of the iron. And that means that if part of the zinc is peeled off, the iron still will not rust, because so long as the zinc is touching the iron, it is the zinc that will react, not the iron. Sacrificial protection. In this case, we have a block of more reactive metal just next to the iron or touching the iron. And so long as it is touching the iron, so we have a block of magnesium or a block of zinc, so long as it is touching the iron, the more reactive metal is the one that will lose electrons and become oxidized instead of the iron. Electroplating, of course, means covering the metal with another metal. So if I don't want my iron spoon or steel spoon to rust, I cover it with silver by electroplating using electricity. The layer of silver on the spoon, of course, will prevent the steel from rusting. The other main topic is extraction of metals. Remember, metals are extracted from their ore. So what is ore? It is the raw form of the metal obtained from the earth. So the raw form of the metal obtained from the earth is called an ore. And from this ore, I can decide to use a specific method to extract the metal. Now, the method of extraction depends on the reactivity of the metal. There are two methods of extracting metals, either electrolysis or reduction with carbon. If the metal is more reactive than carbon, then it will be extracted by electrolysis, because if it is more reactive than carbon, then the carbon cannot displace it from its oxide. But for metals that are less reactive than carbon, I don't need to do electrolysis. I can just do reduction of the oxide with carbon, because in this case carbon is more reactive than the metal. It will displace it from its oxide. So if we're doing extraction of aluminium, remember aluminium is more reactive than carbon, so I have to use electrolysis. You have to remember that the ore of aluminium is bauxite. Bauxite is aluminium oxide, hydrated aluminium oxide. So I take the bauxite and heat it to remove the water. It becomes aluminium oxide, or what we call alumina, and we do electrolysis of that. I need to do electrolysis of molten aluminium oxide, because if I do it as a solution, it will give me hydrogen instead of the metal. So we do electrolysis of the molten aluminium oxide in order to get the metal. But then aluminium oxide alone melts at a very high temperature, above 2000 degrees Celsius. So they found that if they add something called cryolite to this molten aluminium oxide, the melting point is lower. So if we say, why are we adding cryolite? To lower the melting point of aluminium oxide. Electrodes are made of graphite, which is mainly carbon. And if we do electrolysis of the molten aluminium oxide, the aluminium metal will be collected at the cathode, and at the anode I get oxygen gas. Remember that these electrodes are made of carbon, so if you form oxygen gas at the anode, the electrode itself will burn to form carbon dioxide gas, and that is why the anode has to be replaced from time to time. So if he says, why is it that the anode has to be replaced from time to time? Because it burns in the oxygen that is formed at the anode to form carbon dioxide gas. Uses of aluminium, depending on the use, you need to specify the property that we use it for. So if we say we use aluminium for food containers, why do we do that? Because it resists corrosion, it's not poisonous, it does not react with food. If we say we use it for aircraft bodies, that is because it has low density and it is strong to withstand pressure. If we say, why do we use it for overhead cables? Because it has low density and good conductor of electricity. If we say, why is it used for cooking utensils? because it's a good conductor of heat and does not react with food. Are we paying attention? Okay. Extraction of iron. Now you should realize that iron is below carbon in the electrochemical series, so I don't need to extract it by electrolysis, which is a very expensive process. I can just extract it by reduction using coke, which is a form of carbon. The ore of iron, you have to know the ore of iron is hematite, Fe2O3, iron 3 oxide. So the ore of iron is hematite, which is iron 3 oxide. We do this in a huge blast furnace. At the top of the blast furnace, the things we put into the blast furnace are coke, limestone, and the ore, which is hematite. And at the bottom, we put in hot air. So if he says, what are the 4 raw materials used in the blast furnace? It is coke, limestone, hematite, and air. The first reaction that happens in the blast furnace is the coke burns in oxygen to give carbon dioxide gas. What is the importance of this reaction? It is a very exothermic reaction, so it helps to raise the temperature of the furnace. Then, because we have a lot of coke, the carbon dioxide will be reduced by the coke to give carbon monoxide. And it is the carbon monoxide that will reduce the ore. So the carbon monoxide is the reducing agent in the blast furnace. It reacts with the hematite, which is Fe2O3, to give iron plus carbon dioxide. The iron collects down at the bottom of the blast furnace in the form of molten iron. But so far we have not mentioned limestone. Remember, we put in limestone at the top of the blast furnace. Why do we put it? To remove impurities. And you should realize limestone is calcium carbonate. Now, when it goes into the blast furnace, the heat of the blast furnace will change it into lime, which is calcium oxide, plus carbon dioxide, which comes out as waste gas. Where do the waste gases come out from? Can you see? The waste gases come out from the top of the blast furnace on the side. So this lime that is formed will react with the main impurity in the iron, which is sand. And you should realize that sand is silicon dioxide. Now, calcium oxide, which is basic, reacts with silicon dioxide, which is an oxide of a non-metal, so it is acidic, to form a salt, which is calcium silicate. Calcium silicate is slag, and slag will float. Can you see where it floats on top of the iron in the blast furnace? So the slag is that blue thing indicated by the blue one in the blast furnace. This is calcium silicate or slag. It floats on top of the iron and prevents its reoxidation. So I don't want the iron that has been formed to react again with the oxygen in the air and be reoxidized. So that is the function of the slag in the blast furnace. Also, when I remove the slag from the blast furnace, then it is used in road making, like what? Like bitumen. Then this molten iron that comes out of the blast furnace is not pure. We need to purify it and change it into steel. So we take it into another furnace and we pass what into it? We pass oxygen and calcium oxide into it. The hot oxygen is bubbled through the molten iron. It oxidizes the impurities, because what are the impurities? Carbon forms carbon dioxide gas and escapes. Sulfur forms sulfur dioxide gas and escapes. And then the other impurities are acidic impurities. So we add the calcium oxide, which is a base, to neutralize the acidic impurities, form slag that floats on top of the iron and is removed. I can then take that molten iron and add the required amount of carbon and other metals to make the different types of steel. You should realize, what are alloys? Alloys are mixtures of metals and other elements formed by mixing the molten metals together and then allowing them to cool. Why are alloys stronger and harder than pure metals? Because the atoms of different sizes prevent the layers from sliding over each other easily. Remember, we said metals are malleable because the layers of positive ions can slide over each other. But when you have atoms of different sizes, then this prevents the layers from sliding over each other easy. Different types of steel. You should realize that the word steel is just an alloy of iron, carbon, and other metals like chromium and nickel. And as the carbon content increases, the steel becomes stronger and harder. So if we say the steel is harder, that means it has more carbon in it. The types of steel: mild steel, this is a low carbon steel. It's used in car bodies and machinery. High carbon steel, that means it is steel that has a lot of carbon. It's used to make cutting tools and machinery. And stainless steel is used in making cutlery. Okay, alloys of copper. You should realize that copper has two alloys, brass and bronze. So copper and zinc, that is brass. It is used in ornaments. Ornaments mean small things that we put just for decoration. And the buttons of the soldier's uniform, these are made of brass. Bronze is an alloy of copper and tin. Remember again, alloy means mixture of metals. So mixture of copper and tin, they make up bronze. They are used again for ornaments and for making coins. And that's the end of this. I hope this wasn't too long for you, but I hope it's useful. Please try and study all of these things and go over them again. And good luck in your exam. Thank you.